we're almost done with the semester. This is the last midterm before we jump into the final. Just some brief words about the final exam in this class. We were able to ask Dr. Macedoni if the final exam would indeed be similar to the one that we took, because it looks like this semester there has been a lot of disconnect from the previous semesters as to what the exams have been like. We had a lot of free response and you guys have had mostly multiple choice. That being said, your final, it should be the same type of test. It would be the same situation. Ours was 100% multiple choice. My personal experience, Corbin's personal experience, Taylor's personal experience, and everybody that I personally know, their personal experience on the final was that covered a lot, but it was all of the main points of every specific chapter, so it wasn't a complete buster, right? So if you put in the effort to have every chapter down in terms of the main concepts and you can solve those problems, then I would feel good about it and know that the final definitely felt like it was a different test than the midterms, and in a lot of ways the individual problems were easier, but what makes any final hard is that it's cumulative and there is just so much material. So that's something that you just have to conquer on your own, but just know that it felt like it was an easier test, okay? Alright, so to start in with what my section is going to be on today, what I'm going to go over is electroplating, specifically the math problem. So there's a little bit of memorized stuff that's going to be on this test, things like different types of semiconductors, what are conductors, insulators, and things like that, and semiconductors. But the math portion is what I'm going to cover first for the first half an hour, and I'll stop in the half an hour mark, and we'll turn it over to Corbin, who's going to go over the conceptual parts of any type of battery cell, be it voltaic, electrolytic, or any type of cell, and the conceptual nature behind those, and concentration cells and things like that, okay? But before I jump into solving the electroplating problems, I want to highlight this equation right here. This is the bread and butter equation to solve almost all of the math problems that we've done so far in SmartWork, and that will have anything to do with any of these batteries that we're going to go over here, right? The Nernst equation. Okay, so you guys have done a ton of practice, so it would not be worth our time for this 1 hour to do a bunch of problems involving this equation, because you've seen a ton on SmartWork. But we have other types of problems that you haven't seen a ton of, okay? But this equation, you need to know this inside and out. So I'm going to briefly say a few important key things about this equation that are one-liners that you should either memorize or understand conceptually why this is the case. Number one, if you have a concentration cell, right, which we're going to get to what all that is later, but if you have a concentration cell, E naught for this equation will always be 0. Always. You don't have to be told anything beyond it is a concentration cell. Or just look and it's a concentration cell, E naught is 0. Okay? The next thing is if you are at equilibrium of any type of cell, be it concentration and any type, right? Any type of equilibrium condition, your battery stops working. It's done. It's dead, right? There is no more forward reaction or movement of electrons in these batteries. So this voltage potential of your cell is 0. This one is 0, right? And so any type of cell, if it says you're at equilibrium, this value immediately becomes 0. And this Q is now a K. And you guys are pros now with ice tables, Ks and Qs, understanding the difference between those two, right? At equilibrium are Ks. Q and K stand for the law of mass action, products over reactants, right? That's what this whole piece is here. N stands for the number of electrons transferred. A little note about N right here. You always choose the number of electrons transferred between the two half reactions, their least common multiple, right? So don't pick, like, if one half reaction transfers 5 electrons when you balance it, and the other half transfers 2, the N is not 5, it's not 2, but it is 10, right? You always choose N would be the number of electrons transferred as if you were completely balancing a redox reaction right at the end when you want your electrons to cancel one another, because you guys have done a lot of problems with this too. That is the N. Now, most of the time, there's simple half reactions or simple oxidation reduction reactions where you can just see immediately that it was 2 electrons. Oftentimes it is 2 when we get involved with this equation. But if it isn't 2, don't pick the lower number, don't pick the greater number, pick their least common multiple. So if one half reaction is 2 electrons, the other one is 4, it is 4, right? So any situation like that, just to get that out in the open, that is the way, okay? Because I know that can be confusing. Okay, so basic oxidation and reduction is all it is equations where we're looking specifically at a transfer of electrons, who loses electrons, and which pieces gain them as a reaction proceeds. So it'll be up to you to be able to look at a reaction and determine who was oxidized, who was reduced, therefore who is a reducing agent or a reductant, those are synonymous, or an oxidant or oxidizing agent, right? All of these pieces should sound very familiar. Also being able to write out what is the specific oxidation state of the particular pieces of the reaction, right? And notice that is different than saying who is oxidized. Oxidation states is something we assign to every individual piece and give it a specific oxidation state, right? But who is oxidized is a more general term. So as we look at this, first thing we notice is it's sometimes difficult to choose where do you begin, where there aren't any legit charges out front, where it's like clearly this is positive or clearly this is negative. We first, in a situation like this, have to assign the oxidation states. Number one, most of the time our anion takes precedence and we decide to give it its charge first and what it would normally be, right? Oxygen would be a 2 minus. So over here we have a -6. So 2 of these, right? This is a 3 plus. Iron is a 3 plus oxidation state. Notice there isn't a 3 plus up here, but that's its oxidation state. As I look to the right here, I have iron solid, right? So iron went from being completely positive to solid, right? So it has no charge whatsoever. So it had to gain electrons to get to that point. So it was therefore reduced and is the oxidizing agent or the oxidant, right? So I know you've done a lot of practice with this. The only point I want to make right now is this. If you are asked to predict who is reduced in this equation, you would not say iron. You would say this piece. As a group, that compound is reduced, right? So don't say iron. Unless specifically it's like what specific atom, or it lists you out like the options, and it's like, okay, the iron is obviously the one that did all the work. But if it's basically in oxidation reduction chemistry, you choose who is oxidized or reduced are whole pieces, right? So this was reduced, this is oxidized, and oxidation states are the individual pieces we're looking at.
Is O always going to be 2 minus?
Yeah, it's almost always 2 minus, almost always, right? I couldn't think of a situation where it isn't, but generally, actually who you assign first, the order is any of the first 2 metals, the first columns there, those are the 2 that get their charge, you would assign that first. Any of the transition metals, they vary, right? But we don't get situations where that usually gets funky.
Will there ever be a situation where one of the atoms is oxidized and one is reduced, or vice versa?
So you could get a situation like where these 2 split somehow, and then over here you notice that those are the 2 that changed. Then in that case you would say this molecule it was oxidized, but parts of it was reduced as well. Probably wouldn't occur for us, but if that was a situation, that's what I would do. Okay? So we're moving on from this because this is kind of like the basics of oxidation and reduction. You guys have seen a lot of this. We're going to jump right into the heavier stuff for the next 20 minutes. Okay, number 1, we're talking about electroplating right now with me. Electroplating, to get this out in the open, all they will ever be is a type of dimensional analysis problem where you will have to do conversions. So knowing the conversions is essential, right? There's almost no way you can just read an electroplating problem not knowing any conversions and go, okay, that makes sense. I know what I'm doing, right? It doesn't. But if you know the conversions, you can start to begin with something you were given, anything you were given, and see what you can work out to get to a potential answer, right? So conversions that are necessary is understanding what an amp is, right? An amp is a coulomb per second. Understanding what a volt is. A volt is a joule per coulomb, right? And understanding what a watt is a joule per second, okay? Between those three conversions, there's not a single electroplating problem you cannot solve. So I threw together several, and they are not hard because honestly, they all just run through these. But I want to walk you through how you do these, okay? This first one. How many grams of silver can be deposited in that amount of seconds, so that amount of time, at 0.05 watts and 1.984 volts? So we're given all this stuff, right? How much grams of silver? What do we know about silver? Well, I know that it's Ag. I could look at the periodic table, maybe get its molecular weight. I also might recognize that silver usually just becomes a 1+ cation. That's all I've ever noticed. So you'll notice in electroplating problems, they kind of expect you to understand silver would become 1+. It would lose 1 electron when it does electroplating problems, okay? So I can immediately get that down. I'm given the amount of time necessary to plate out. I'm told watts and volts, these completely abstract units to my mind, right? Watts and volts. It's something that is difficult to sit there and be like, oh, I understand now what a volt is. It's the potential. It's like how many joules are on a coulomb. Well, that's what it says. But, you know, it's hard to figure that out, right? So what I like to play is just a complete units game. We just got to play a units game. Number one, the way that you transfer anything from mass or an amount of an element, be it how much grams, how many moles, the piece that gets you from mass amount, gram amount, into these types of situations, watts, volts, amps, is coulombs. Coulombs is the king. If you can get anywhere to coulombs, you have Faraday's conversion between coulombs and moles of electrons, and you can shift into a weight amount of an element. Coulombs. If you get lost, try to get yourself to coulombs, okay? So, right now, we don't have anything close to coulombs, but we have watts and volts. Here's the trick. We know that the unit for watts is joules per second. We know that the unit for volt is a joule per coulomb. So if I wrote that out, a joule per second divided by a joule per coulomb, or maybe I'll write this clear and say a joule divided by a second divided by a joule per coulomb. So look how weird this gets. Okay, so if I divide by this, is the same as multiplying by the inverse. So now I'm going to take this over, and I'm going to go, okay, I'm going to actually multiply, instead of a joule per coulomb, a coulomb per joule. What happens to the units here? Joules cancel, and what do I get? Coulombs per second, which is amps. So taking watts and dividing it by volts gives you amps, right? Right there. So an amp is not just a coulomb per second, but it is a watt volt. See all this weird stuff? So if you were given that, we got amps. And when you get amps, we're getting close to coulombs. So we're looking really good, right? So what I'm going to do now is just bust through the dimensional analysis, and we're going to move on to the next one, because that was the specific point that I wanted to make. Okay? So, busting through the dimensional analysis. Okay. Is it cool if I erase these conversions? Are we good? I should have that down. All right. So what I understand as of right now, that if I take the 0.05 watts and divide it by the 1.9841 volts, that will leave me with 0.0252 amps or coulombs per second. Okay? My handwriting sucks. You guys already know that, but just try to stick with me here. So, I know how many seconds that I'm going to run this reaction for. This number right here. So if I do that math out, now I'm left in just coulombs, which is the king. Right? I get to coulombs and everything is getting easier. Okay, so then I'll get to coulombs and end up with 326.59 coulombs, and now it's just smooth sailing. I know that for every 9, 6, 4, 8, 5 coulombs, I have 1 mole of transferred electrons. Right? That's Faraday's. This is a memorized piece. That's that puzzle to switch you to it, right? Now, I'm dealing with silver. And what do we say about silver? It's always a 1+ cation. So for every 1 mole of electrons that get transferred in silver, I should end up with 1 mole of silver. right? And I know that every 1 mole of silver weighs 107.868 grams. There's that full piece of dimensional analysis start to finish. Notice that it's not completely clean. What I mean is I had to chunk this out to get this, multiply that to get that, and then it continued to the end. But all of the units cancel. Coulombs with coulombs, moles of electrons, moles of electrons, moles of AG to leave me in grams. The answer to this problem is 0.365, and then a bunch of other stuff, grams. Okay? All right, so highlighting that an amp is also a watt divided by the volts. Okay? All right. Say that again. It's just how it reacts chemically. So I know it's unfair to feel like, was I supposed to know that? But it feels like it's hard for us to recognize that because we've done so many problems. We're like, yeah, silver's 1. But it's just how it chemically reacts, and they will expect you to know some of those things. I can't hear you.
Which ones will they expect us?
So SmartWork does a good job at highlighting the same type of element that we would use over and over. They do it pretty well. Like nickel, they'll do silver, they'll do gold. Between silver and gold, those two are used a lot. So with gold, a lot of times they'll tell you gold 3+. But with silver, they don't like to say it, but it's always 1+. So that's the one that probably would get you. All right. Okay. Let's look at this problem. This is a heavy word problem, even though I parsed it out in just chunks of what the problem would say. I didn't write it all out on the board so that it's easier to read this way anyway. Okay, yeah, just settle down just a little bit so we can hear better on the video when we watch this back, okay? All right, so a chemist. So here, I'm going to say the word problem in my head to you, right, what I have in my mind about this problem. Because this is how these question stems are usually worded. They're a little bit wordy. So a chemist, her goal, this chemist wants to plate out a solution of nickel sulfate. Okay, her goal is to plate out 40 grams of nickel. The problem is that she starts her work at 7:30 a.m., but she has to be finished and she gets kicked out of the building at 6 p.m., right? They close the building up. So what current should she run this reaction at so she can plate out enough of the nickel, her goal of nickel for her day's work? What current does she need to run at? So start with your ideas. I'll give you a minute to think about this. That's what it is. It's the lingo. Current is amps, but you should know that. Just knowing the conversion. Okay, I know I barely gave you time to even write it down, probably. But let's talk about this. If all I want to know is the current, which is the amperage, right? However you say that. Okay, I know that is a coulomb per second. I need to know how many coulombs I need to pump into this thing for every second that goes by. So if I know how many seconds I have in the day, that's important. And how about how many coulombs are going to be required to plate 40 grams of nickel? Well, let's say I have 40 grams of nickel. Let's start with a piece that we know. I have 40 grams. Let's get that bad boy to moles here. So I know that for every 58.69 grams of Ni, I get a mole of Ni. Okay, well what about this solution? So for every 1 mole of Ni that I get, how many moles of electrons get switched around here? If this is the solution? 2. Exactly. 2 electrons. 2 moles of electrons. And we knew that because sulfate is a 2- anion, right? And so this had to be a 2+, but just took 1 of them. So it was losing 2 electrons to do that whole process. So 2 moles of electrons are going to cruise over. And then here's that key piece. the conversion is that for every 1 mole of electrons, I get 9.6485 coulombs. So doing this little chunk of math out will leave me in coulombs. Sweet. So if I do that, I'll end up with 131518.14 coulombs. Now to get amps, what do I know about amps? Amps is coulombs divided by the amount of time that I have. Well, I started at 7:30 a.m. and I had till 6 p.m., which is 10.5 hours. But we're not looking at amp hours or anything like that. We just want to know per second. So if I can take my 10.5 hour day, and I know that for every 1 hour, I can solve for how many seconds I'm just going to go by in my day. And I can take that number and plug it in right there and just do the division and get my amps. So how much time went by in seconds? Well, it was 37800 seconds. Right? Doing just the conversion of how much time did she have. And then plugging that in. Right? Just letting this math click through in your calculator. You should get an amp amount of 3.48 amps to run to make this happen for her. Okay? That's not too bad, right? So here's the point. Will you push this one up, Corbin? Here's the point, you guys. When I'm here in front of you, you guys are getting used to seeing Corbin and I, and maybe used to your TAs talking about these problems. It actually seems pretty easy. I know you're like, well, that's not too bad. But here's the thing. I know from personal experience and from talking to students that you kind of get in there and read a problem, and it feels like it's completely different from anything you've ever tried. So go in there with some weapons. And that weapon for you, for electroplating, will be coulombs. Figure out how to get to coulombs and use the Faraday's constant. 1 mole of electrons equals 96485 coulombs. And that will flip you to some mass amount of an element and let you make those conversions of electroplating, right? If you are lost, just throw down the value you know, 40 grams. And if I just try to get myself to coulombs, all of a sudden I'm like farther in the problem and realize I'm close to an amp if I just know the time that went by. And then I can just do it. Okay? Wow. All right. So for the last 5 minutes, actually just do this on your own, right? For the last little bit of time, and then we're done. I'd like you to try this one now that I've given you my whole spiel about coulombs. But here's your chance. How many hours will it take to plate out all of the copper in a 200 milliliter solution of a 0.15 molar concentration of Cu2 plus at 0.2 amps? I want all of that copper gone. I don't want any aqueous copper. I want it all to be solid. I want to plate that thing. Okay? If you're not sure where to start with something you know. Maybe the amp part, or solve for how many moles of copper are there. And start rolling with that. This might be an important little tip-off, right? How many electrons would get transferred? Things like that. Spend a couple minutes. I'd like you to do this one, and I'll throw the answer up on the board before we switch to Corbin. keep working on it. Okay. All right. So I'm just going to write the answer. And if you got this, great. If you didn't, just circle it. And I don't want to show you how to do it. I'm actually not going to. Because it's actually easier than the last couple. It's one little segment of dimensional analysis. But I want you to work on this problem until you get there. And when you get to that, if you didn't get it when I'm about to write the answer, if you don't get this value, I want you to work this problem before you go to bed tonight until you get there. And then do it over and over. And be confident. Memorize those steps you took to get here. Because these are the big steps that help. These are like really crucial steps that you take in almost any electroplating problem, okay? So it should take about 8.04 hours. Okay? All right. Work on that, okay? And here's the other thing. You know we stay after for a little bit, and if you would like me to show you individually, I would love to. But I think it'll be more of a benefit for you to work to this. Work to this on your own, okay? I'm going to push the bench over. I'll look at it. Go ahead.
Okay, so switching gears, the first thing that I'm going to go over is balancing a redox reaction, okay? This is something that you should probably just have down by now. And balancing a redox reaction is something that no one should ever miss on an exam, because you can always check to see if you did it right. So I want everyone in here to commit that they will not miss the balancing problems on the test, because you can always check to see if you did it right. And I'm going to go through different steps. So if you want just like an easy go through, different steps to follow and memorize, we'll do it that way so you can get it down. So first of all, here's my reaction. Here's my redox reaction, okay? So step number 1 in balancing a redox reaction is to separate the half reactions. Okay, separate the half reactions. So this one's pretty easy. Basically, like things go with like things. So sulfite is going to go with sulfate. So that's my first half reaction. SO3 2 minus to SO4 2 minus. My next half reaction is MnO4 minus to Mn2 plus. Okay, step number 1 is complete. Step number 2, and the way that I normally do these, I normally balance one half reaction all the way through, and then do the second one all the way through. If you try and do all these steps for both of them at the same time, you're more likely to make a mistake. If that's the way that you've been doing it, by all means, but I think you have a less of a margin to make a mistake doing it this way. So step number 2 is balance O's with H2O. So doing this first one, I'm just going to balance my oxygens, and I balance my oxygens with water. So I have 3 oxygens on the left, 4 on the right. I need 1 more on the left, so I'm going to add 1 H2O here. Step number 3, balance H's with H plus. So, going back to this first one, I've got 2 H's on the left, none on the right, so I need to add 2 H plus here. And I forgot to mention, we're doing this in basic conditions. I'm going to show it to you in basic because it just involves one more step. Acidic is a little bit easier, so I thought we'd do the harder version. So we're doing this in basic conditions. Okay, so balance H's with H+. Step number 4, and this is only if it's basic. If you're in acidic solution, just completely skip this step. Okay? So step number 4 is to cancel H+ with OH-, and you have to do this on both sides. Just make a mental note. On both sides. So as of right now, everything's balanced. Sulfur's balanced, hydrogens are balanced, oxygens are balanced. This thing's happy, except for charge. So, and the fact that I have H+ when I'm in basic conditions. That can never happen. If I'm in a basic solution, it's impossible for H+ to exist. So what I do is I cancel those H+ with OH-. Yes?
This might be kind of a weird question, but how do we know when we have to do something to both sides and then we can just add, like for example, when we're adding water, how come we don't like have to add water to both sides?
Because if you added it to both sides, then the oxygens would be unbalanced together. So the whole point of adding water was I want to balance the oxygens. So if I added 1 oxygen on both sides, I would have 5 over here and 4 over here, so they still wouldn't be balanced. So once everything's balanced, like it is right now, now I'm in a state where if I add anything to one side, I have to do it to the other, because everything's balanced as of right now. So I'm going to add 2 OH- here. Now these two things are going to cancel each other out to make 2 H2O. Those will just react with each other to make 2 waters. And if I do, and so this is the only step you do to both sides, is the OH. So if I do that, then I add 2 OH- here. And again, everything is still balanced here. Oxygen's balanced, hydrogen balanced, sulfur's balanced, everything's good. Step number 5 is to balance charge with electrons. So I want to calculate the total charge on both sides of the reaction. Okay? So, total charge on the left is 4-. This is 2 times this minus, and this is a 2-. So I have a total of 4- on the left. On the right, I have 2-. So, where do I have to add electrons? Yep, on the right. So they both need to be 4-. A lot of people have been confused thinking that you have to get the electrons to 0. The electrons don't have to be 0 on both sides. They just have to be the same. So if this is 4- and this is 2-, then if I add 2 electrons to the right, then both sides are 4-, which is what we want. So add 2 electrons here. This half reaction is now balanced. Everything's done. So let's do our second one now. So for step number 1, there's a step 0. I forgot to write here. Step 0 is to balance all non-oxygen and hydrogen elements. So balance all non-oxygen hydrogen elements. Yeah?
Can you cancel one of the H2Os from the left?
Yeah, we can. You can do that now, or I can just do. I was going to do it later, but yes, you could do it right now if you wanted. Okay, so what I mean by this balance all non-oxygen and hydrogen is that, say for example, I had 2 MnO4 here and 1 Mn2+ here. To balance this, I would have to put a 2 Mn2+. Okay, you see this mostly when you have like a Cl2 or a Br2. The reduction reaction for Br2 goes to Br-, but if I was going to write that, I'd have to have 2 Br-. So that's where that comes in. Balance everything that's not oxygen and hydrogen. In this case, we didn't have to do that because the sulfurs were balanced and the manganese are both balanced here. So, going to step number 1, we separated it, so balance O's with H2O. I've got 4 oxygens on the left, none on the right, so I have to add 4 H2O on the right. Step 3, balance H's with H+. I now have 8 hydrogens on the right, none on the left, so So I'm going to add 8H plus. And again, we're in basic, so I'm immediately going to cancel those H plus out with OH minus. So I'm going to add 8OH minus. Those are going to react to form 8H2O. And adding OH minus on the left, I have to also add it on the right. Final step, balance electrons. Okay? Total charge on the left is -1. Total charge on the right is -6. This is an 8 minus plus 2 minus 6. So I have 1 and 6, so I have to add 5 to the left. Here's a checking point, okay? This is something to write in your notes. If you're balancing a redox reaction and you feel like you've completed both half reactions, this is one thing to check to make sure you're on the right track. If the electrons are on opposite sides of the arrow, you're doing good, okay? If you're doing this and you find that your electrons are on the same side of the arrow, you did something wrong and you should start over, okay? So this is a checking point. In this, we've done this correctly because I have electrons on the right over here and electrons on the left over here. Step number 6 is to combine reactions by canceling electrons. So now for this very last step, what we're going to do is we're going to combine both of these reactions. I'm going to combine everything on the left, I'm going to combine everything on the right, and we're going to make one final redox reaction. The thing is, I can never have electrons showing in my redox reaction. The electrons have to cancel on both sides. So what Braden was talking about is we have to find the least common multiple between these two electron numbers to get them to cancel. In this case, with 2 and 5, that's going to be 10. So what I have to do, this one's 2, so I have to multiply every coefficient in this reaction by 5. So just hang with me here. I'm going to do some erasing. So this is going to become 10 OH minus, 5 H2O, 5, 5, 10 waters, and 10 electrons. And now for this one, I have 5 electrons here, so I have to multiply this whole thing by 2 to get these electrons to cancel. So I'm going to have 10 electrons, 16 waters, 2, 2, 8, and 16. So once we get our electrons to cancel, now we can start combining these things. And like someone mentioned, we have a lot of waters going on here. So what I can do is just start canceling them out. You can do that after you balance the half reaction, or you can do it now. Doesn't matter. Either way is good. So just to reiterate something that Braden said, what is the N here in this reaction? If I was going to solve for the E of the cell at non-standard conditions, what is N? 10, okay? 10 is the number. It's not 2, it's not 5, it's the least common multiple between those two. Okay, in this case it's 10. Did you have a question?
That's exactly what
Okay, good. So let's start canceling stuff out. So on the electrons will cancel. Some of you probably already done this. So on the right I have 16 waters, and on the left I have 21. So I can cancel all of these waters. This was 18. So I have 18 and 21. So cancel all 18 over here. If I cancel 18 over there, I have to cancel 18 over here. That's going to leave me with 3 total waters. Okay, next we can cancel OH minus. I have 16 OH minus on the right, and I have 10 on the left. So I'm going to cancel all 10 OH minus on the left, cancel 10 on the right. That leaves me with 6 OH minus. And that should be good. So now, final thing, let's write out our redox reaction. So I have 5 SO3 2 minus plus 2 MnO4 minus plus 3 H2O goes to 5 SO4 2 minus plus 2 Mn2 plus 6 OH minus. Now this is why you should never ever ever miss a redox reaction, because you can check. Yes.
You know, let me just ask, are the H2O and the OH minus typically going to be on opposite sides?
It kind of depends on everyone.
Okay.
You kind of just have to work with whatever it comes out to be. So what I would do here now is go through and check all of these. So I have 5 sulfurs, 2 manganese, 2 manganese. Go through and do all that and check the charge as well. If no one's objecting to this, then I think we did it right. So I'll let you guys go through that one again. Any more questions on balancing? So again, this was basic. So if you have acidic, the only thing you don't do is put OH minus in there. Leave the H plus and go straight to electrons. Okay. Next, we're going to talk about voltaic cells. We're probably going to go like maybe 5 after because we got a little late start because of the little magic show. But yeah, it's okay. So next, we're going to talk conceptually about cells. In this case, we're talking about a voltaic cell. A voltaic cell is probably the easiest one to understand. And once you understand a voltaic cell, an electrolytic cell is really easy. Yeah? It's low battery. Let me know if it goes out, then I'll put mine in.
Let me just see the video.
It's still ticking.
If it goes blank, then I'll plug mine in. And we'll have to do 2 parts.
I don't know, just roll.
Yeah, we'll just keep going. Okay, so voltaic cells. So voltaic cells are 2, basically like these are solutions and these are metal pieces. Now the whole idea with a voltaic cell is that there's going to be 2 metals that have different reduction potentials. In this case, I didn't tell you what the reduction potentials for zinc and copper are. But I'll just tell you, copper has a more positive reduction potential, which means what? It's going to be reduced, okay? So when you're looking at those standard reduction potentials, the one that's most positive is the one that's reduced. So it's going to be our cathode. So what that means is that electrons are going to flow from this side to this side. And I'm going to explain exactly how that works. In a voltaic cell, the whole thing that drives the electrons and drives power to be generated is that these metals have different reduction potentials. The electrons naturally want to go to the cathode. So zinc is the anode. What's happening here is that zinc metal, zinc solid, if you see it in the equation, is being oxidized into zinc 2+. So this metal is shooting zinc 2+ ions into the solution. When these ions are created, there's excess electrons now left on that zinc metal. So what happens is those electrons will flow through this wire to this other side, in this case the cathode. So now on the cathode we have excess minus charge. And what do we know about copper? Copper really wants to be reduced. So these copper 2+ ions see these extra negative charges on this metal, and they just come slap right onto it. And that's called reduction. So that these 2+ ions are getting deposited onto that cathode metal. So in essence, what's happening here is that this anode is going to shrink over time. It's going to get oxidized because it's constantly losing ions to the solution. Whereas this thing is going to get built up. Okay? Since ions are depositing onto this copper, it's going to get larger. Yes?
Why is the anode negative again? It's losing electrons.
The anode is negative because electrons are negatively charged and they flow towards the positive. It's negative because there is excess electrons there. That's the easiest way to think about it.
Okay.
Yep. Okay, yes.
So when you see an actual battery that has like the plus and the minus, does that actually correlate with which is the cathode?
Yep. Yep. Okay, so voltaic cell. This one's probably the easiest to understand. The only difference in an electrolytic cell is that this thing would be run in reverse. So if electrons naturally want to go from zinc to copper, but let's say in this case I want to plate something on the zinc. The way that I do that is that I have to hook this cell margin up to a battery, and that battery is going to force the electrons to go the other way. So it's against the natural will of the two metals. So now the electrons are flowing this way, and the zinc is going to get reduced. So in electrolytic cells, the E of the cell is always negative. In voltaic cells, the E of the cell is always positive. Yes?
Which way to the battery? Like the
No.
negative charge?
No, these could be on, it doesn't, like the anode doesn't always have to be on the left. It can be flopped.
But like if you were to do, so if you put a battery on top to reverse it doesn't matter which side you connect to the battery.
The electrons will always flow towards the positive. Or if it's electrolytic, the electrons will flow towards the negative. So it's opposite of what they normally want to do. Normally electrons go from the negative to the positive. If it's electrolytic, they will go from the positive to the negative. Yes? Yes. Yep. Yes. Yeah. In a voltaic cell, the cathode is positive. Yep. Yes.
And so then in a voltaic cell, when there's not a battery involved?
Correct.
But
There's
in
no
the
battery.
one there is.
It's just the natural tendency of the electrons to want to go that way. Yep.
Is there a possibility there being an electrolytic cell that doesn't reverse the flow, it just speeds it up or something? Like, can you put that in the question?
I don't think so. That has to go the opposite way. Yeah.
What aspect or characteristic of the battery is it that, because I imagine that there's the natural flow, right, and it wants to go that way, so what about the battery has to be stronger in order to reverse the current?
What about the battery?
Yeah.
It's just the fact that the battery, you hook the battery up in a way that it forces the electrons to go the other way, because the battery produces a current which just pushes the electrons the other way.
But what if the natural tendency of the voltaic cell is stronger than like the wattage or something of the battery?
Then I'm not really sure, but I think then it wouldn't do it.
Right. So,
Yeah.
So would it be like the wattage or the voltage or what?
I don't think you're going to see something like that.
Okay.
I think if it's an electrolytic cell, you can assume that the electrons are going the other way. Yeah. One more question, and then we got to move on.
Does that have to do with the energy potential of the battery? So the energy potential on the negative side of the battery is lower than the EU plus?
I'm not really sure. This is kind of more of a physics thing. Like if you want to get really into the details of these batteries, I recommend you take Physics 106 because you will do this very extensively. For the case of this class, this is all you have to know. So don't worry about all the details. Yes? Okay, no. The cathode is always the site of reduction. It doesn't matter what the charge is on it, the cathode is always the reduction site, the anode is always the oxidation site. So if it was going in opposite, if this one was being reduced, yes, this would now be the cathode, and this would be the anode, because it's going in reverse. The cathode is negative now. Yeah. So the charge always stays the same. This will always be negative. This will always be positive. Yeah. Okay. That was a lot. Okay. Next thing is concentration cells. Concentration cells are different from voltaic and electrolytic cells because there's not two different metals in them. It's the same exact metal in either case. So there's not a natural tendency of reduction potentials to want to flow electrons one way. But if we vary the concentrations of ions in these solutions where this anode and cathode is, then we can get electrons to flow, even if they're the same metal. Okay? So looking at this, which is right the cathode or is left the cathode? How'd you know that? You just guessed that I would switch it? Yeah.
The more dilute is always the anode.
Good. The more dilute is always the anode. And you can conceptualize this because this has a low concentration of lead. This has a high concentration of lead. So just thinking about gradients, this lead is not going to want to pump more lead ions into here if the concentration is already so high. But this one will, because I have such a low concentration of lead ion that this one is totally fine getting oxidized because it wants to pump more ions into the solution. So what happens here is that the anode will increase the ion concentration of the solution and the cathode will decrease. So my electrons are going to flow here. I'm going to get excess electrons over here on the cathode, and then those lead ions will deposit. So essentially what's happening here is I want to form an equilibrium. I want these concentrations to be the same. And once those concentrations are the same, no electrons will flow anymore, and this thing is dead. So it's just a natural tendency for this thing to want to reach equilibrium. That this one is going to get oxidized, and this one's going to get reduced. That's all you have to know about a concentration cell. Yeah? Good question. It's always dilute over concentrate. Okay? When you're doing the Q in these equations, it's always dilute over concentrate. That's a really big thing. Yes?
So the more concentrated side is getting reduced?
Correct. Yep. Because I want to decrease this concentration, so those things are going to stick onto the metal. And I want to increase this concentration, so those things are going to come out into the solution. Yeah?
You don't have to put a battery on both.
Nope. No battery. Yep.
Which side would be positive and which side would be negative?
So if the electrons are flowing this way, then this would be positive. And that would be negative. Yes?
What do we need to understand about like the tube and the NO3?
Okay, so this is a salt bridge. So what a salt bridge? A salt bridge basically allows, mainly for like voltaic and electrolytic, it complexes what's happening. So if you look at the voltaic one, I'm constantly pumping plus ions into the solution. So what the salt bridge does is it pumps negative ions into the solution to complex with those plus ions. That's helpful because if I pumped enough plus ions into the solution, it would get to a point where that metal no longer wants to be oxidized because there's so many ions already in there in the solution. So what the salt bridge does is it lets that gradient still be there because I'm constantly pumping negative in there, so that anode will constantly oxidize. Okay, switching gears into chapter 18. There's a couple things we need to talk about. Metals, semiconductors, and insulators. You guys, so I wrote metal. You could also write conductor here. This would be conductor, semiconductor, insulator. So, what you need to know here is that metals exhibit an electron C model. What that means is that the electrons are just spread out like a C in the metal, which allows those electrons to move around really easily. So electron movement is what lets electricity and things conduct. It lets electricity flow. A semiconductor has a full valence band. And what I think all the extent that you have to know about this is that when two things come together, they form bonding and anti-bonding orbitals. the valence band is the bonding orbitals. And in this case, they're full. The anti-bonding orbitals are empty. This is the conductive band. And notice here, the only difference between a semiconductor and an insulator is this gap. So essentially, for a semiconductor to start conducting electricity, electrons are going to have to go from this valence band up into the conductive band. So the reason this is a semiconductor and this is an insulator is simply because of this energy gap right here. It's easier for electrons to make that small jump than for electrons to make that huge jump. And that's why insulators will never conduct electricity, because the electrons simply can't make that jump to get into the conductive band. Okay, there's 3 types of semiconductors that you need to know. And this is where we talk about impurities or doping semiconductors. So what I can do is I can take a semiconductor and I can dope it to make it conduct much better than it normally would alone. So there's 2 types. There's an N-type and a P-type. So this is the intrinsic. This is just like your standard semiconductor. Everything's normal. Full valence band, empty conductive band. So an N-type semiconductor is when I add extra electrons. So let's say the most common semiconductor that we probably see is silicon. So counting silicon's valence electrons, if you go over, it's 1, 2, 3, 4. Okay, 4 valence electrons. Let's say I have silicon. I take some of that silicon out of my semiconductor and add phosphorus. Phosphorus has more valence electrons than silicon, so what's going to happen is it's going to form an N-type semiconductor. Once this valence band is full, the only place for the electrons to go is up to the next level. So this is an N-type semiconductor where we're adding more electrons than this valence band can hold. And the other type you have to know is a P-type semiconductor. A P-type semiconductor is the exact opposite of an N-type semiconductor. We're going to take electrons out. So again, if I have a silicon semiconductor, silicon has 4 valence electrons, and let's say I dope it with boron. Boron has 3 valence electrons. So I pull some silicon out, put boron in, there's now going to be deficient electrons in there. There's not going to have that full valence band anymore. So we get this gap right here. So because I have empty space in this valence band, these electrons now have the ability to move around, and they will conduct electricity much better than it would if it was just completely full. So these are the 2 types that you have to know. Yes?
So does P-type conduct better than the intrinsic?
Yes.
Okay.
Both N and P conduct better than the intrinsic. The whole idea of this is that we're making a semiconductor conduct better. Yes?
So which would conduct better, N-type or P-type?
Oh,
Is there an answer to that?
I don't think so. I mean, there might be, but for the sake of this, I don't know, and I've never heard it explained, so yeah.
So we wouldn't want to try to make a P-type semiconductor by taking silicon and adding aluminum back from that, because aluminum is a metal and would then turn it into
Yeah.
then was turned into a full metal.
Yep. Yep. Good thinking. So, I think this is basically the extent that you have to know. We didn't get, in this semester, we didn't really get to go into really in depth of this stuff. So I think the questions that you're going to be asked are going to be of a more simple level than what we've seen previous. So the last thing that we're going to talk about is LED lights. LED lights work because there's 2 semiconductors. Specifically, there's an N-type and a P-type semiconductor. So what LEDs do is that we have these semiconductors. I have an N-type that has excess electrons. These dots right here are meant to represent electrons, okay? And P-type is deficient in electrons. One way that you can think about P-type is that there's positive charges here. I'm deficient in electrons, so I have positive charges here. So as you know, the electrons, they love positive charge. So they want to come down here and get in that p-type. They want to be there. But what we have to do, since these things are separated by this like transition space, is we have to force those electrons that way. So what an LED light does is it induces a current which makes the electrons move. As the electrons move this way, they will then get in position to where they can drop down into the p-type. And you guys learned in Chem 105 that whenever an electron drops in energy, energy is emitted. And in this case, it's a photon. So when one of these electrons drops from the conductive band to the valence band, a photon is emitted. Now we can vary what color that photon is by changing how big this energy gap is. If I want a violet LED, then I'm going to make this energy gap really big. If I want a red LED, then that energy gap is going to be small. The energy of the photon will be correlated to the energy gap that electron is dropping. It's like the simple Bohr model that you guys have seen since Chem 105. Okay, any questions on this? LEDs, yeah.
Just back to the N-type and the intrinsic, distinguish between those two, because you're adding in both.
Yes. So intrinsic is a full valence band, meaning this thing can't accept any more electrons. This thing's completely packed. And it doesn't conduct electricity very well because the electrons can't flow. You might get some that jump up. Semiconductors, they're semiconductors, so they conduct some, but not great. So when I add extra electrons in there, since this is already full, the only place they can go is up to the conductive band. And then once these ones are up here, look how much space they have. They'll conduct really well. It's a semiconductor. Not as well, yes. Quiet down, guys. Just one more question. You know that? Probably. I don't remember.
Just if it says pure.
If it's
silicon,
yeah, if it's pure silicon, then it would just be intrinsic.
I don't know what percent like decrease from pure is when it. I think they added a pretty good chunk.
Okay, good luck, guys. Did it stay valid?